Okay, well, in a previous mini lecture, we talked about one of the fundamental laws of physics in terms of conservation, and we talked about conservation of momentum, and that momentum is conserved in a collision, in an interaction, really as a product of Newton's third law. Well, there's another fundamental principle that I want to introduce you to in this very short mini lecture called the conservation of energy. And similarly, just like in the case of our conservation of momentum, conservation of energy says the same thing. It says that no energy can be gained or lost during a situation, during a time period of an object in motion, of an object in state. And in the case of conservation of energy, it's in everything. Nothing. And energy is never lost. It just changes what it looks like. So conservation of energy is that there is no loss of energy for an object, for a system through time. All right, so that energy only changes form. So, for example, let's say we have an object that's moving along, has some kinetic energy, and it runs into a wall. And now it's not moving. Well, it appeared to have lost its kinetic energy. It's no longer moving. So during that phase of going from moving and going to not moving, what happened? If conservation of energy exists, what happens to that energy? Where did it go? If I am no longer moving, it had to go somewhere. Well, when it hits that wall, we hear something. Energy is converted into sound energy. When it hits that wall, we may hit the wall and it might break apart a little bit. So energy is transferred from one object to another. And so now that object has energy. Work was done on it. Now it has energy. It came from the other object. Perhaps it heats up. There's a little bit of heat generated when we have that collision. So some of the energy goes into heat. So energy is always converted from one type to another. There's lots of different types of energy, but we really only focused on two of them in our introduction of energy, our mechanical energy. And indeed, we're going to focus on the conservation of mechanical energy specifically. So we are not going to lose energy to heat or to sound or to some of those other things. And what we're going to be thinking about, if I'm in an isolated system where I won't lose energy to heat or to sound, there's no external forces acting on the object as it changes state, then we can look at its mechanical energy, the conservation of mechanical energy. So how does that look? That means that the kinetic energy and the potential energy of an object has to remain the same throughout time. So let's look at a roller coaster. So let's imagine that you're over at Valley Fair in the Minnesota area, and you're in this roller coaster. And if we think about, here you are in the car, if we think about what happens in a roller coaster, let's say that we get to the very, very, very top of that roller coaster. We're barely moving. Well, this roller coaster is up high. If it's elevated and we identify perhaps a height equal to 0, let's identify our height equal to 0, the very bottom of the roller coaster. What happens as this roller coaster, as you and your car go through the roller coaster ride? Well, right now we have some height. And we're just barely moving, so let's pretend we're starting just at the very, very tippy top, ready to be released down this motion. Well, as my height decreases, am I losing energy? Well, I'm losing potential energy, but what happens at this state? Well, at this case, at this day in the game, I'm now moving, so my velocity or my speed is greater than 0. Which means I've lost potential energy, but I've gained kinetic energy. As I continue to go lower and lower on the track, I lose more and more potential energy. But what do we know happens? I gain more and more speed. So I'm increasing my kinetic energy. As I go through the roller coaster ride, I convert my potential energy to kinetic energy. And I get here at the bottom of my roller coaster ride, right at height equal to 0. And I'm the fastest I will go, because now all of my potential energy, which is now 0, has been converted to kinetic energy. And what happens as I crest the second hill? Well, I start to gain some height, which means I've gained potential energy, but I also know that I start to slow down. So I've lost that potential energy has been obtained from the loss of kinetic energy. And as I go a little bit higher, I gain more potential energy, and I've slowed down even more. That potential energy comes at the loss of kinetic energy. And this cycle continues on and on. Every time I gain potential energy, it's as a result of losing kinetic energy. Similarly, as I move lower and lower in my path, I lose potential energy, but I gain kinetic energy. That's the idea of conservation of energy. Now we can take that idea and we can put it into a relationship, a mathematical relationship, because we like to do that. We like to talk physics in math language. So what does this mean? Well, it tells us that the energy at the beginning, the energy at some initial, the total energy at some initial time is equal to the total energy at some final time. Whatever that time may be, through time, the energy doesn't change. So if my initial time is at the beginning of the track, and my final time is halfway down the ramp, fine. The energy didn't change. The energy isn't lost during that time. Or if my initial time is at the beginning of the track and my final time is when I'm at the top of the second hill, great. The energy didn't change during that time. So how this initial and final is defined will depend on how we're looking at the analysis and what we are interested in knowing about an object and what an object is doing through time. Well, that total energy, that's total mechanical energy. So it's made up of our kinetic energy at the beginning plus our potential energy at the beginning. Whether you use G, P, E, or U, the idea is that we're dealing with the mechanical energy, so gravitational potential energy in this case. And that has to equal the total energy at the end, so the final kinetic energy plus the final potential energy. If I were to rearrange this relationship and think of it in a different way, bring all of the variables to one side, I end up, I'm going to go in this direction. I subtract potential energy from both sides, and I subtract kinetic energy from both sides. The relationship, if I take everything off over here, I'm left with 0. My final kinetic energy minus my initial kinetic energy, well, that's my change in kinetic energy. My final potential energy minus my initial potential energy, that's my change in potential energy. And this is a way we can think about the idea of conservation of energy in another mathematical type relationship, that all the change in kinetic plus all the change in potential has to equal 0. So what I add to kinetic, I must lose in potential. Or what I add in potential, I must lose in kinetic. So that the net change is equal to 0. So we can think about it in two different mathematical representations. The idea being that energy of a system, and in this case the system is just a single object, it never changes. And it only changes form. And in the case of mechanical energy, which we're going to focus on, looking at the kinematics and the motion of an object, that total energy must remain the same at every point in time. And we can choose to define those points in time based on what we're interested in analyzing. All right, conservation of energy. Good job.